morning everyone. So, the last class we talked about fixed effects model. We actually derived, we took the null hypothesis as means are equal and equal to 0, and null alternate hypothesis at least one is not equal to 0. It is a fixed effects model. So, summation of tau I equals to 0, and we actually derived what is the expected value of sum square treatment, and we showed what is the expected value of sum square error as well, and the overall sum square total is divided into two components, sum square treatment plus sum square error, right. That is the first derivation we saw. So, that the total variation in the data is due to two components, two orthogonal components, that is very important, right. One is the variation due to noise, the other one is variation in the treatment. The treatment, it should be simple, the treatment variation is nothing but x yi dot bar minus y bar dot, that is the overall variation minus the variation due to the ith treatment squared deviation, and then within a treatment the variation is mainly due to noise. So, these two are orthogonal. So, the sum square total is literally divided into two parts, and these two I say are orthogonal because you remember the cross terms going to 0, right. So, that is why I said these two are orthogonal to each other. Make sense? Clear? Okay. So, that is what about our last class the important ideas we saw, and then we towards the end we said the F test, which is a ratio of mean square treatment to mean square error, should be good because the treatment expected value of mean square treatment is composed of two components, one is sigma squared, the other one is tau I squared, and remember if tau I equals to 0, tau I square is equal to 0. So, you will have the expected value of mean square treatment to be sigma squared, but if at least one tau I is not equal to 0, then summation of tau I square will be greater than 0, and because tau I square is always positive, and therefore your F ratio will be greater than 1, and that is what we statistically test. And remember, this is where probability and statistics connect well. If you look at, we could have calculated sum square treatment alone, but we would not have done any hypothesis testing. Why? Because without probability you will not know what is the expected value of sum square treatment. Then how do you conduct a statistical test? You will not know what is the ideal value of the ratio. You can take an F test, but what is the ideal value of F? When tau equal to 0, when sigma tau, when each tau has 0, what is the final value of F? You will only know when you know the expected value of mean square treatment. Okay. So, you could have done everything from the data up to sum square treatment calculation and mean square treatment calculation from the data, but beyond that if you want to test the hypothesis, that is where expectation comes into picture, because I need to know the final theoretical value of expectation of mean square treatment, so that I could take a ratio and then say my F test is valid. That is, F test will give me 1, F will be equal to 1 when tau equal to all tau equal to 0. That is only possible because I know the expected value of mean square treatment, right. The expected value of mean square treatment was composed of two parts, right. One is sigma square, the other one is the summation of tau I square. What if it is sigma squared by something else? Then you cannot use F test, you understand. What if it is sigma squared instead of an addition? What if it is a multiplication? Then tau goes to 0, the entire term will go to 0, right. So, you need to know the theoretical expected value, the theoretical averages, okay, and that is where probability comes into picture. Now, you understand where the expectation is a probability concept, it is not a stat. Stat we only talk about samples, sample mean, but the population idea comes into picture everywhere. Clear? So, now having said that, so the last class we did look at the degrees of freedoms, and then we also solved a simple problem where we computed, I gave you the formulas for computing the sum square treatment, sum square error and sum square total, and sum square error is nothing but total minus treatment because they are orthogonal basically. Error and treatment are orthogonal, the cross terms went to 0. So, there is no correlation, linear relationship between them. Okay. In fact, when A dot B equal to 0, what does it imply? When you say the inner product or dot product is 0, when will it happen? When they are perpendicular. Okay. So, error and treatment are perpendicular. Okay. So, now the next step, of course. So, once I know that I have let us say I know that the null hypothesis I could reject. Let us say I am rejecting the null hypothesis. What is the next question you will be asking? Let us say I rejected the null hypothesis. What is my next question? Which treatment is not 0? Now you know one of the treatment is not 0. Next obvious question is which treatment is not 0. So, how do I proceed with this? How do I do? Which treatment is not 0? So, we need an estimator of treatment mean, right. The estimator of treatment mean is what? Yi dot bar, right. For each treatment the estimate is yi dot bar is a estimator of mu I hat, is actually a point estimator of mu I hat is yi dot bar, right. Now, of course, we have assumed earlier beginning that the errors are normally distributed, okay, and what is the mean? Mean is mu I, and what is the variance? Sigma squared by n for each treatment. For each treatment there are n samples. So, the variance of the estimate is what? X bar, the variance of x bar is what? Sigma squared over n. So, that is the same idea. So, your yi hat, what are you assuming? Your yi dot bar, you are assuming it to be normally distributed with mu I and sigma square over n. Okay. If I know sigma squared, then I can construct confidence intervals, right. If I know sigma squared, then I can construct confidence intervals. What will be the confidence interval? Mu I will lie between whatever yi dot bar plus or minus t distribution or z distribution depending upon the degrees of freedom. If you have more than 30 degrees of freedom, it will automatically become normal distribution. If it is less than 30, remember the underlying population assumption is what? Normal. All of this is under the assumption the underlying population is normal. Then it becomes automatically a t distribution. So, you have t alpha by 2 or t of minus alpha by 2 with n minus 1. What is the degrees of freedom for treatment? And noise, what is the degrees of treatment for noise? A into n minus 1 is the degrees of freedom for noise. So, that is what I should be using, right. So, you have, so what will be the I need an estimator of what I call sigma squared. Okay. How do I do an estimator of sigma squared? Only I know an estimate of, remember sigma squared is not given to you. Usually what will you do? You will replace with yes. In this case, how do I replace? What do I do? There are multiple variables, there are multiple populations, right. If you remember two sample, in two sample you have two population, here you have 5 to 6 populations, right. You are comparing 5 to 6 treatments. So, each of the treatment comes from a different population. The good part, if you remember, is I assumed that their variances are equal. So, I can go and do what is known as pooled variance estimator. Remember, in two sample distribution we had two cases, when sigma 1 square equals to sigma 2 square and when sigma 1 square not equal to sigma 2 square. When sigma 1 square equals to sigma 2 square, we can compute what is known as pooled standard deviation and pooled variance. That is what we will do. Okay. So, we are going to do what is called pooled variance. Any questions? What is it? How do you get a p value? So, p value is the value at which you could reject the maximum confidence with which you could reject the null hypothesis. Okay. So you have to go and look for not the 95 percentage or 99 percentage. What you should do is whatever value you get, for that you go and look at the inverse, then you will get the p value in the table for in the table. So you have to go and check, you check with your friends, you in one way, none of you know how to do p value. This is just trivial looking at a table, okay. This is not a something conceptual. Concept is p value is simple idea is the maximum confidence with which you could reject the null hypothesis, okay. You may set out at 95, but the answer may turn out to be 99.99 or whatever, right. So you look at the whatever value you get and then go and look at the corresponding PDF, CDF value, okay. So that is your p value, okay. So probably you can help her out, okay, that's fine. So now you can give confidence intervals only when you know sigma squared, right. You need an estimate of sigma squared like S squared, right, but this is not one population, so you cannot take S squared, it is more than one population, in fact many variables. So what we do is, since all the variances are equal, we do what is called as pooled estimation, MSE, okay. So mean square error. So you can look at your what I call your 2 sample population, you have did your pooled estimator, that is the same idea, okay. In 2 samples, when you compare 2 populations, you did your pooled estimator, the same idea you do pooled variance here, okay. So this is nothing but actually it will turn out to be nothing but your mean squared error. So what is the estimate of variance is nothing but your mean squared error. Instead of sigma square you replace with MSE. Mean squared error you are calculating, right, sum squared treatment, sum squared total. So sum squared error, sum squared total, sum squared treatment. So sum square error is nothing but what, sum squared total minus sum squared treatment. How do you get mean squared error? Sum squared error divided by degrees of freedom. What is the degrees of freedom? A into n minus 1. For each column you have n samples, so n minus 1 degrees of freedom because you estimate 1 mu. So there are totally a rows, so a into n minus 1. So that is the degrees of freedom for error, okay. So the total mean squared error is going to be what? Sum squared error divided by a into n minus 1. That is my mean squared error, okay. So now I can give a what? Confidence limits for each mu I. So for each treatment mu I can give confidence intervals. Now look at it all in one shot, we do not do multiple, all in one shot. I can give confidence intervals all in one shot. So mu I is plus or minus yi bar, yi dot bar plus or minus t alpha by 2 into square root of MSE divided by n, that is all. And the degrees of freedom is a into n minus 1. If it is greater than 30, it automatically becomes z alpha by 2, that is all we have, right. So now we can give confidence intervals for mu I dot, okay. Once you give confidence intervals for mu I, can you not do hypothesis testing, whether it is significant or not, whether mu I is greater than 0 or not, can I not do hypothesis testing? I can do hypothesis testing also, okay. Once the confidence interval is there, what else? You know the entire PDF, you know the acceptance region, you know the rejection region, you know the confidence limits, you can give what is called as the what confidence, I mean you can give hypothesis, do hypothesis testing also. It will boil down to single sample. Now you are going to test for what? Each mu I is, which mu I is greater than 0 or not, at least one of the mu I is not equal to 0. Then if you construct confidence interval, the confidence interval should be giving you an idea. Suppose my confidence interval is this, okay, plus 0.5 mu 1, which is greater than 0, mu 1 or mu 2 is greater than 0, most likely. I have two confidence intervals written, mu 1 is lying between minus 0.5 to 0.5, another one mu 2 is lying between 0.5 and 1 confidence limit. Which one is most likely that greater than 0, whether mu 2 is greater than 0 or mu 1 is greater than 0? You understand why mu 2? By 90 confidence interval, if you put 95% confidence interval, you can say 95% of the time it is at least greater than 0. Whenever a confidence interval encloses a 0, that typically means it is 0, you do not need to consider it. So mu 1 is actually 0, why? 0 lies within the interval. So you can assume that mu 1 is 0 because 0 is lying within the confidence interval, whereas in case of mu 2, 0 is not within the confidence interval. So that means mu 2 is the most likely candidate which is not 0 compared to mu 1. Mu 1 is technically, actually statistically mu 1 is 0. Whenever a confidence interval encloses 0, that means the quantity is statistically 0, you understand. So this is also very important when you choose parameters in your machine learning algorithms today, whatever you call hyperparameter tuning, all of the machine parameters when you take, whenever a confidence interval of the parameter has a 0 in it, that means that parameter is 0, you can throw that away, you understand. So your parameter, your bound, the confidence interval should not enclose 0. If it encloses 0, that means the parameter is statistically 0 and not useful. Okay. So mu 1 is 0 here statistically, whereas mu 2 is not 0. So just by even constructing the confidence interval, you can know which one is 0 and which one is important, which treatment is important and which treatment is not important. Make sense? Clear? So you can now do 2 population, 3 population, whatever you want to, 2 population also. 1 population we did multiple, then you can construct confidence interval, then you can do individual hypothesis test, or you can do 2 sample hypothesis test, that is whether the difference in mean is significant or not, that you can do, right, because sigma 1 square is we know as MSE, sigma 2 square is also MSE. So you will have 2 sigma square which is 2 MSE divided by root n, that is all. You can now do single population, 2 population test also, that is you can check for whether individual mean is greater than 0, you can construct confidence interval first and then you can check whether individual mean is greater than 0, you can do hypothesis testing, or you can check whether the difference between the 2 treatments is greater than 0 or equal to 0. Okay. So a lot of tests, single and 2 sample test can be done once you do ANOVA. ANOVA is like the first step actually. When you have multiple treatments, ANOVA is the first step. You do the ANOVA and then say look, at least one treatment is important. Then you can construct confidence interval and try to pick out which treatment is important. Then you can go ahead and do a statistical confirmation and say that this treatment is statistically significant, that is all. Make sense the overall flow. So we went the inverse way, we started with 1 sample, 2 sample and built ANOVA, but ideally when you apply it will be the inverse, because you start with many population, many parameters and many population from various populations, then you boil down to which treatment is important. So it will be always the inverse. Understood?